Okay, we're going to do the second part of the Chapter 8 unit in your book, and which is 8.2 and 8.3, which starts on page 696. We're dealing with permutations that now have repeats. And remember, permutations is the fancy word for multiplying, so it's not a big deal. So don't get the word stuck in your head. But if you take a look, the difference between a combination and permutation is that in a permutation, order is the important thing. That's what's key. And then going back from the last lesson, just a quick reminder what factorial notation is, because we're going to be working with that more significantly this unit, or this section. And factorial notation is simply taking a number and multiplying it down to 1. So if you had 15 factorial, that would be 15 times 14 times 13, all the way down to 1. And then whatever the number 15 factorial is, you'd pop that into your calculator and you'd figure it out. So here's a situation where a permutation deals with what's in order. So if I want to figure out how many different ways these four people can sit in these chairs, I have to take a look at how many possibilities for each specific location. So if I take a look at this chair, say take a look at the first chair, like so. Well, how many different people are available to sit there? Well, there's 4 people here, so I could choose any one of those 4 to sit there. So there's 4 opportunities or 4 possibilities of people sitting there. And so let's say I move this person to that chair. Okay? Which now means for the next chair in line, there are 3 people available. Okay, so move that person there, which means now there's only 2 available here. So let's say we bring this girl here, which now means that there's only 1 available for that. So how many different ways can people sit there? I have 4 times 3 times 2 times 1, which is 12 times 2, which is 24. Or you could say 4 factorial, and that would be 24. Okay? So now we're going to take a look. I just want to make sure I'm on the right page. Yep. Okay, so now we're going to take a look at what happens when repeats aren't allowed. Now, repeats in your book, in the work text, they call identical objects. So in this particular case, there's 4 completely separate individuals for 4 different chairs. Well, now what happens if you've got identical objects within the set? For example, here's a word, tooth. Well, within the word tooth, there's 2 O's and there's 2 T's. So if I want to figure out how many different ways I could represent those letters in a combination of 5 different letters using T, O, O, T, H, I'd have to figure out or consider that there are 1, 2, 3, 4, 5 factorial ways those letters can be rearranged. But what we have to understand is that there's 2 T's that are identical. So if I put them in this order, so I put them in that order, and I switch those 2 T's into different spots, I'm going to get the exact same word, the exact same combination, because these 2 T's are identical. Same thing, I could change the order of the 2 O's, and I'm going to have the same word. So in this case, what we do is we take the 5 factorial, and we divide whatever is identical and how many there are. So in this case, it'd be 5 factorial, divided by 2 factorial, and another 2 what the heck happened there? Another 2 factorial. Okay? So that's how we would deal with those. So if you take a look at the next example here, and this is the next page in your handout, how many ways can you rearrange the words these? Well, there's 5 letters in the word these. So that's what this considers. But I have to take into consideration there's two E's that are identical. Call them repeats if you want. And because they're repeated, we have to divide them out, because when I switch the order of those two, I get the exact same answer. So it's the same combination. So then I just go 5 factorial is 120 divided by 2 factorial. That gives me an answer of 60. So if I take the word Keith, where there's 5 different letters, well, the permutation or the number of different arrangements for this would be simply 5 factorial, which is 120. But in the word these, because there's 2 E's, we have to divide out the 2 E's, which is 2 factorial, because they can be arranged 2 factorial ways, and I'll explain that in a second. And then you get 60. Okay? So if you take a look at the word reference here, reference has 9 letters, but it's got 2 R's, and it's got 4 E's. So instead of dividing, taking 9 factorial and dividing by 2 and then 4, what we do is, I'm just going to open up a new page here. If I've got reference, and I've got 9 factorial ways, and I divide out the E's, well, the thing is, there are 4 of them. And for clarity's sake, let's name these 1, 2, 3, and 4. Well, how many ways can I rearrange those numbers? Well, I could arrange them. I could put any 4 of them in the first spot, any 4 any 3 in the next spot, any 2 in the next spot, any 1. So there's actually 4 factorial or 24 ways that I can rearrange these numbers, which then means there's 24 different ways I can rearrange these E's. Now I know they're all identical. You say, doesn't matter which order they're in, but you have to consider that if this is 9 factorial ways I can rearrange those, then there's 4 factorial ways I can rearrange those E's alone. So I have to divide out the 2 factorial for the R's, because there's 2 R's, and I could have R1 and R2, and then rearrange them to R2 and R1, and 4 factorial ways for the E's. Okay? So when I look at that, here's how I get my number. I get 9 factorial. So I just calculate out what those calculations are, and then the answer is 7,560. Okay? Now, if you take a look, not there yet. All right? So then, say take a look at the word Hawaii, and here's an example. Here's Hawaii, and I can rearrange this I can put it over here, and I can put this one over here, and I'm going to get the exact same word. So I have to divide those out. Same thing with the I's. I can take this I, change positions of it, and so I've taken 2 different characters, rearranged them, but I haven't changed the combination of the actual entire word. So in this case, it'd be 1, 2, 3, 4, 5, 6 factorial divided by 2 factorial divided by 2 factorial. Okay, and then I could calculate that out. Again, here's the word Toronto. Well, Toronto's got 7 letters in it, so that'd be 7 factorial, and that would divide by 1, 2, 3 O's, and there's 3 factorial ways those things can be arranged, and 1, 2 T's. So that's how many ways you can arrange the word Toronto, the letters in the word Toronto. So if repetitions are allowed, then it's pretty easy. I mean, for example, if you got this example, there are 9 switches on a fuse box. How many different arrangements are there? Well, fuse switches have 2 possible positions, on or off. So this one could be on or off. Whoops. This one could be on or off. This one could be on or off, and so forth. So it's just all 2 times 2 times 2. How many different 3-letter words can be made if you're allowed to repeat the letters? Well, I could put any of 26 of the letters in the first position. I can put any 26 of the letters in the second position and the third. So what you have to do with repetitions and in your work text, they call them identical objects and different objects. You have to look for identical objects. And if there's identical objects, then you have to divide them out. And if there's not, then you just multiply your way through. Okay, so that's kind of one section of 8 point, I think that's more 8.3 than 8.2. 8.2 deals more with when you've got a permutation of a group where there's more objects than there is actual people. And we call it a subset. So let's say this lady runs away. Okay? And we've now got 5 chairs for 3 people. So that's the set that I'm trying to fit into the objects is smaller. So we call this permutations with subsets, where the set that you're trying to fit into the group is smaller than the actual available spots or positions. So in this particular case with the picture, there's 5 positions, 5 chairs available for only 3 people. Well, how many different ways can I rearrange them? Well, I could put one person here, which would leave me with 2. I could put one person here, which would leave me with 2, or with 1, and I could put one person here. And you're going to say, well, there's 2 different chairs left over. So here's what we do. Take a look and say, well, how many different places can any of these people sit? Well, there's 5, so if this is the one I'm going to choose, she could sit in 5 different spots, right? So let's say she chooses that one. So she's got 5 different places to locate to. Which means now that this person only has 4 choices to sit. 4 spots she can sit. And let's say she sits here. And then this dude right here can sit in 1, 2, or 3 positions. So let's put him there. And there's only 3 positions available for him, which is 5 times 4, which is 20 times 3 is 6. So there's 60 ways. So instead of 5 factorial ways, now there's only 60 ways those people can sit because there's 2 empty spots. And that's what we have to consider. Now the good thing is, there's a formula for this. And the formula is, if I've got a permutation where order matters, and I've got 5 spots available, I'm going to call those available spots or available positions in, and there's only 3 people in the subset, and I'm going to call the subset R, my formula simply is NPR. Now the great thing is your calculator will do this for you. There's an NPR button in your calculator. So when you go to find, if you've got a graphing calculator, and you go to find the N factorial button, this button here, the NPR and NCR, when you get to combinations later, are both found in the same spot. So in this case, in your calculator, you just go 5, type in 5, and then you go find your NPR button, push it, and then 3. Because in this case, there's 5 available positions for only 3 people. Oops, for 3 people. So it'd be 5P3. And that's how you would say it, 5P3. So 5P3, if you pop that in your calculator, should equal 60. So permutations can be written in this particular form. And here's the formula to do any permutations where there's subsets involved. NPR, N being the total number of available spots, is the combination of that and the number of people or things or objects in the subset. How many things you want to fit into N. And so the formula is a fairly simple one. It's just N factorial over N minus R factorial. And that what that does is, if you take a look at our chair example, we had 5 people. So we had NP5, or sorry, we had 5 people for 3 spots. So in the chair example back here, we had 5P3. So if I calculate that out using the formula, I get 5 factorial over 5 minus 3 factorial, which would be 5 factorial, and this is in brackets. So that's going to be 5 factorial over 2 factorial. Okay? Now the great thing about factorial notations, and I'm going to insert a page here, is that if you've got 5 factorial over 5 minus 3 factorial, you can simplify that pretty quick without using your calculator. Because 5 factorial over 2 factorial would be 5 times 4 times 3 times 2 factorial, it's simplified there, over 2 factorial. And the 2 factorials divide out, which leaves you with 5 times 4 times 3. All right? So if I had a, say, 7p4, and I asked you to figure that out without using a calculator, you could use the formula n factorial over n minus r factorial, which is one you do not have to memorize. And I would get 7 factorial over 7 minus 4 factorial, which would leave me with 7 factorial over 3 factorial. And if I simplified this out, I'm just going to take 7 and start multiplying it out like factorial notation does. And I'm going to stop right there, right where it matches the denominator. Because now I'm just going to divide those out. So I'm left with 7 times 6 times 5 times 4. And you say, well, I can't do that. Well, sure you can. Let's work backwards here. 5 times 4 is 20. 20 times 2 is, 20 times 6 is 120. And then 120 times 8 is 840. So 7p4 is 840. Now, obviously, if you have the opportunity to use your calculator, you will. You just pop that in your calculator, and you should get the answer of 840. But there are going to be some equations that you have to work out, and I'll show you here in a second, that you're going to have to use this exact philosophy on simplifying down. Okay? And that's the next step. And it's probably the hardest of this whole little section. Okay. So arranging subsets of objects. Here's, there are 10 people in a competition. Okay? How many ways can the top 3 be ordered? And so I've got 10 people in the competition. That's my full set. And my subset would be 3 because there's only 3 people. Top 3 is the only 3 that I care about. So how many ways can 3 people be ordered out of 10? Well, if you take a look, and this is in your handout, there's 10 people that could be in the first position, which means then if the one person's out, there's only 9 people left to be in the second position, which would then create a space of only 8 for the last position. All right? And so you could take 10 times 9 times 8 and multiply it out. And again, if you took 10p8, you'd get the exact same answer, 720. All right. So example 2 is down here. It says there are 12 movies playing at a theater, and how many ways can you see 2 of them? Well, 12 is your total number available, and 2 is the subset of how many you're going to go see. So my combination is going to be 12p2, or sorry, my permutation is going to be 12p2, or I can just go 12 times 11, just draw it out. Either way, you get an answer of 132. So here we go with a couple of examples. In a game of Scrabble, Eva drew the letters A, W, L, N, S, O, and D. How many permutations of 4 of these letters are possible? She's trying to create a 4-letter word. How many different 4-letter words, whether they're words or not, just how many 4 different permutations of letters are there? Well, she would count, and let's do this in blue. There is 1, 2, 3, 4, 5, 6, 7. So NPR is going to be 7 factorial over, and I only want 4, so it's going to be 7 minus 4 factorial. So we get 7 factorial over 3 factorial, which is coincidentally, no intention at all, the one we just did. So you would pop 7p, you could do 2 things. You could pop 7p4 into your calculator, get the right answer. You could solve it out and do it this way and get 7 factorial divided by 3 factorial in your calculator. In either way, I think, if I remember correctly from a couple minutes ago, the answer is 840. How many ways can 3 grade 12 students, 3 grade 11 students, 4 grade 10 students, and 2 grade 9s be seated in a row if the grade 12s must sit at each end? All right, now this is where it gets a little complicated, and you've got to be able to think. What I like to do is I like to draw this out. There are, in this case, there are 3 grade 12s, 3 grade 11s, 4 grade 9s, and 4 grade 10s and 2 grade 9s. There's 12 kids. Okay? And how many ways can they sit if the grade 12s must sit at each end? Well, if I've got a grade 12 here and a grade 12 here, I have to think to myself, how many people are available to sit in this spot? 3, which means only 2 available to sit in this spot, which means there's 10 people left for the entire rest of the seating, and that is just simply, because there's no order or no restrictions on it, simply 10 factorial. Okay? So then in this case, it would just be 3 times 10 factorial times 2, and that would give me my combination. But again, that's just another situation where you've got some restrictions to work out. And a lot of these questions, especially the work text and the exercise book, cause you to create a situation where you're going to have to draw it out and think, and then reduce the number of available students in the entire set. All right. So here's the formula, and this is the next thing we're going to have to do. You're going to have to be able to take a n factorial and multiply it down to 1. And this is all theory, but n factorial would be the same thing as n times n minus 1 times n minus 2. Because if you think of the number 7, if I had 7 factorial, it is 7 times 6 times 5 times 4 times 3 and so forth, down to 1. And what I'm dealing with here is simply reducing by one number. Well, if I don't know what the number is, if the variable they give me is n, well then the next number in the situation is n minus 1, n minus 2, n minus 3. If I was reducing n minus 3, it would be n minus 3 times the next number, which would be 1 less, which would be n minus 4, times the one that's less, which would be n minus 5, and so forth, all the way until you get down to 1, depending on what n is. If n was 65, let's say, I'd have to keep going until I got down to n minus 65, or n minus 64. Okay? So that's how you reduce that. And why do we need to do that? Well, because you've got equations like this that we have to simplify. And what we do when we simplify these equations is take the larger of the two numbers. Now, the trick here is that this is the larger of the two numbers. So I reduce that down so that it matches that factorial number. And all I'm going to do is I'm going to multiply it down, so I got n. The next number less is n minus 1. The next number less is n minus 2. And that is this. So I'm going to put the factorial there, and I'm not going to reduce it down or multiply it down any further. And then I'm just going to multiply or copy this out like so. Well, now these divide out. And so I'm left with n squared minus n when I multiply those two things up together. All right, so this simplifies to n squared minus n. Well, then the next step is they're going to make it equal to 0. And now I've got a quadratic equation that I need to solve. So in this case, I would take the n and factor out, and so there's my factorization of that, and then n equals 0 and 1. So if this equation was n factorial over n minus 2 factorial equaled 0, I could tell you that by doing the algebra and the work that the answer here would give me a value of n equals 0 and 1. All right? The only thing I have to watch for is, does it work? Because 1 is the lowest factorial number possible. So, or 0 is actually. So in this case, 0 minus 2 factorial doesn't exist because there's no negative factorial value, because the lowest number we stop at is 1. 7 factorial goes down to 1 and stops. All right, so here's what we're going to work on. Here's an example out of page 700 in your work text. They've got np3 equals 60. Well, what we're going to do when we're solving this out is we're going to put it into the formula. So it's going to be n factorial over n minus 3 factorial equals 60. Now, I don't like this question because you're going to get 3 answers. And then when you get 3 answers, you're going to have to guess and check. when you get quadratics, it's just a matter of solving the quadratic, which we can do. That's an n minus. So I'm going to reduce the top one. I'm going to expand it out. So I get n times n minus 1 times n minus 2 times n minus 3 factorial divided by n minus 3 factorial. And that equals 60. And so those divide out. And now I got n minus 1, or n times n minus 1 times n minus 2 equals 60, and I got to solve for n. So you have three numbers that multiply together, n minus 1, n minus 2, that equals 60. So the easiest thing to do is guess and check. The numbers are going to be pretty small. And so what the book suggests you do, and you can read it on page 700 on how to solve this out, they suggest you estimate that the cubed root, because you got three numbers multiplying here, the cubed root of 64 is 4. So why don't you start at 4 and see if 3, 4, and 5 work, which they do. But like I say, I don't like the answers where you get the three integers in it because there's guess and check, and I just hate guessing and checking. Sorry, Brian. All right, with this question, you've got the same thing. So now I've got, following the formula, I got 6 factorial over 6 minus r factorial equals 30. Okay? Well, once I got this, I can get rid of the fraction, multiply both sides by 6 minus r factorial, and I would get 30 times 6 minus r factorial. And then I would divide both sides by, both sides by 30. Because I want to isolate that factorial. So I'm going to divide this by 30 and this by 30. So now I can get an actual value for this. 6 factorial, I think, 6 times 5 is 30, 4, I think it's 720. Divided by 30 equals 6 minus r factorial. And so when I get this, I get 24 equals 6 minus r factorial. Oops. And again, I don't like these questions great because now you got to guess and check what factorial gives you an answer of 24. Well, it's 4 factorial gives you 24. So if 4 factorial is 24, then r has to be 2. So there's a little bit of logic and guesswork in there. It's not just straight algebra, which I like. This is perfect for Mr. Brian. All right. So here's what we're going to work on. I know this took 30 minutes. What I would do is I would take and I would go through it piece by piece as you work through the handout and the exercise book and the work text. But we're going to do 712 and do these questions. So I'm doing 3 and 4, A and C only for those two. Same thing here, B and D for all of 3, 4, 5, and 6. And then the rest of these questions, and then these ones. And this is out of your exercise duotang that you have. And these ones will cause you to think. And that's the great thing about permutations and combinations, is they require quite a bit of brain service. So good luck with that. Text me if you're having trouble, and I'll hopefully be able to work your way through it. You might have to take a picture and text because I don't think I'll have my math book with me, but hopefully I can give you a hand. And if I can't, then Mrs. Fickert likely could. Good luck.